Welcome to the Earth Observation Tools tutorial that will be run by Jordi Corbera, PhD on Physics and Head of the Earth Observation Department at the Institute Cartographic and Geological of Catalonia. The tutorial will be run according to the following outline. First, the platform. Second, the sensor. Third, the image. And finally, the mission as the global architecture of an Earth observation tool to transform users' needs into scientists, operational and technical requirements. Just a few words about the history of the satellites as an Earth observation tools. This history starts with the Corona program as an American strategic reconnaissance satellite program to surveillance Soviet Union and Republic of China. But probably from a commercial and environmental and in terms of usability, one of the most important dates is July 1972. With the launch of Landsat 1 program. Landsat program is still in use and represents the most important global database of Earth observation on multispectral basis. Next slide items the main data in terms of the use of satellites as Earth observation tools. You can see following Landsat programs, but basically we would like to point out at the end of 90s with the rise of very high resolution commercial satellites like Iconos or QuickBird. We are talking about commercial satellites with a resolution of 1, 2, 3, 4 meters. In front of the previous spot or Landsat satellite with resolutions about 10, 20 or 30 meters. Another disruptive data is about the end of 2008-2007 with the rise of constellation of satellites like TerraSync or Cosmos Skymet. Constellations offer the possibility of the same sort of satellite and the same sort of sensor at different platforms. So then the revisit times and the possibility to take image is really improved. But also with TerraSync and Cosmos Skymet, we have the possibility to obtain radar information in a few meters, 2-3 meters. The satellite is part of the global Earth observation architecture when we have different parts. Basically, the source of energy, at this figure the sun, atmospheric interaction, reflection, the sensor recording this radiation, and finally how it's sent to the ground station and transformed into products, service, and derived data. Ground segment is a key part of the global Earth observation architecture, basically with a twofold aim: programming and scheduling the satellite and obtaining the telemetry data and mission data to properly offer as an user interface products, service and data. A lot of ground stations are located in polar regions because the orbits of satellites offer more visibility at these latitudes. Broadly speaking, we can divide the Earth observation tools and architectures in terms of sensor and platform into active and passive systems. Active systems offer the energy supply has an owned subsystem on board of the satellite, while passive sensors use an external source of illuminance as the sun. At the figure on the left hand side, we can see an active sensor where the sensor on board the satellite sends an electromagnetic wave, and then how this electromagnetic wave is backscattered by the land at the sensor. On the right, we have a passive platform with a passive sensor with the reflected radiation from the sun is captured. A great majority of Earth observation tools use a passive sensor, so it's a key issue to distinguish which are the main technologies involved in the capture of reflected radiation from the sun. Three main sensor typologies are used in terms of image formation on passive satellite platforms. The whisk broom with a scanning rotating mirror. The push broom has a scan system that uses the velocity and direction of the line of flight satellite and just to take frames as the digital photography. At this animated image, you can see how the image formation is finally obtained with the three main sensor technologies. Talking about the main image typologies, we have four different sort of image formation by using these sensors on board of panchromatic, multispectral or stereo image platforms. Multispectral image or hyperspectral images are images with many channels, normally in the visible and near infrared regions, providing a very interesting spectral information about the objects. Panchromatic images only one wideband in the visible and near infrared region, so are black and white images, but at the same sort of sensor as a source, we have better spatial resolution on panchromatic images than multispectral ones. Pansharpened images are fused images combining panchromatic and multispectral channels. Normally, we use the better spatial resolution from panchromatic images with the multispectral texture of different spectral signatures. And finally, also we can obtain from sensors on board satellite platforms 3D stereo capabilities. These images are normally used to derive or obtain digital elevations models. But where are located the satellites? Basically, we have different sort of orbits in terms of altitude or also in terms of the purpose of the application or the Earth observation tools to be served. We have some synchronous orbits where the satellite is targeting the same Earth surface at the same local mean solar time, or in other words, at the same solar illumination conditions. But also we have geosynchronous orbit synchronized with the rotation period of the Earth, or geostationary orbits that located at 36,000 kilometers above the Earth equator are following the direction of the Earth rotation. This sort of orbit is especially used for telecommunications or meteorological purposes. In terms of altitude, we have low Earth orbit, medium Earth orbit, geostationary orbits. The common use of low Earth orbit for Earth observation is defined with orbits below an altitude of 2,000 kilometers. Medium Earth orbit are normally used for constellations that are providing service of navigation and positioning, and geostationary orbits for telecommunications purposes. The majority of Earth observation platforms are located in circular polar orbits on low Earth orbits, synchronous. So we have two passes, an ascending one and descending one. The ascending pass is most likely on the shadowed side of the Earth, while the descending pass is on the sunlight side. So the satellites based on passive sensors, we can obtain images on the descending path, while, for instance, radar sensors can obtain images on the descending or ascending path because are not sunlight dependent. The sort of application will define the sort of orbit that we need to potentially fit the technical and operational requirements. At the following slide, we have some animations and graphs that demonstrate the advantage and disadvantage of geostationary versus polar orbits, heliosynchronous or geosynchronous. The main difference between both orbits are focused or addressed in terms of coverage and also in terms of footprint and contact time that the satellite and related data are captured on the Earth surface and send it to the ground station. Repeat cycle and revisit period could be defined as the two main specifications in terms of define the potential usability of the satellite platforms, and could be defined as after a number of orbits, subsatellite point retrace his path. or the revisit period or revisit time is the time elapsed between observation of the same point on Earth by a satellite. So revisit is related to the same ground trace, and it's a key issue in terms of frequent imaging or surveillance is required. One of the key technical tools to improve this revisit time is the use of nadir viewing capability. So we can orient the satellite as the platform or the sensor of both to take images at a certain nadir angle. So then we can obtain images on a certain Earth, land or sea target that it's not exactly over the nadir of the tracking satellite line. That's improved a lot the revisit time, as well as the use of constellation, or just both approach of nadir viewing capabilities on a platform constellation architecture. Just to end part 1, some words about the discussion of satellite or airborne sensor as Earth observation tools. Maybe a good schedule or approach to discuss about this point should be to answer these 2 questions. Are satellite platforms the main approach to sense the world? Maybe the answer is yes, because main environmental and climate challenges are at global scales, so needs a synoptic, repetitive, and a stable basis of sensing, and orbits are a very stable, repetitive, and synoptic approach. Yes, because surveillance and monitoring of critical infrastructures and resource management arise as one of the main challenges today, and also offer a capacity to sense any place far from administrative constraints or aeronautical issues. But if we want to answer the question only with satellites the world could be sensed, the answer is clearly no, because major impacts and capacity to apply and assess policies are at local and regional scale, where airborne sensors are a very reactive and sustainable approach. No, because calibration and validation even of satellite data by the in situ components always will be necessary. And it's a critical point on the use of Earth observation platform sensors as sustainable and feasible tools and own capacity to manage and schedule your own platform. The sensor is the main subsystem on board of the satellite platforms in terms of Earth observation architecture. A sensor is a converter that measures a physical quantity and converts into a signal. So, an optical image sensor is a converter, a device that converts an optical images into electronic signal. As has been previously mentioned, we have two main sensors, active and passive sensors. Active sensors are equipped with a transmitting and receiving system that capture the reflected signal on the illuminated surface, whereas passive sensors have only systems for signal reception. So, the first family or active sensors are sensors that represent their own energy source, and the passive ones, the source is the sun illuminated signal. To talk about a sensor is to talk about their main characteristics. So, is to talk about its characteristics in terms of radiometry and geometry. Radiometry is a branch of science that deals with the measurement or detection of radiant electromagnetic energy. It is expressed in terms of digital numbers and represent at the image formation as pixels. And the main characteristic is the dynamic range. In terms of geometry, we talk about the location or positioning of these digital numbers, and the main specification is the geometric accuracy. According to previous definition, a good definition of the pixel is the smallest addressable element in a display device, and the address of a pixel corresponds to its physical coordinates. The next slide shows at different scales the same images the image could be zoomed to finally detect the pixel element and the corresponding values. Talk about the sensor is talk about basic parameters like field of view, ground sample distance, or so on, as well as the dynamic range or the range of values that this radiative detecting level could be transformed in digital numbers, 8 bits, 12 bits, or 16 bits. According to this number of bits, we can summarize the image with a different sort of digital numbers. So we have more or less values to be represented. Talk about the field of view is to talk about the amplitude of the image on the land target that could be imagined, and it's obviously related to the swath or footprint. The relation between field of view and swath is determined by the altitude or the orbit of these satellite platforms. Fixed an altitude and a certain field of view of the sensor, we obtain a fixed swath or footprint on the Earth surface. According to the sensor detector, who is responsible to transform the radiative values into a signal, we have a different ground sample distance. or broadly speaking, a spatial resolution. Until now, we have been talking about radiometric or geometric characteristics. What about spectral characteristics? A multispectral image or a multispectral sensor is one that contains data at the specific frequencies, spectral regions or spectral bands across the electromagnetic spectrum. The wavelengths may be separated by filters or by use of instruments that are sensitive to particular wavelengths. Each region is a spectral band or channels. The spectral resolution or the number of spectral bands will become a key issue in terms of usability and applicability. Because if we have, as this example, 8 spectral bands like worldview 2, we are more sensitive to obtain values, digital numbers, and to transform into a signal about the behavior or how the surface reflects the sunlight at different spectral or wavelengths. So we can obtain information more detailed about some sort of covers and behaviors, as is shown at this slide, how soil, vegetation, or water are sensitive, reflected the sunlight at different visible near infrared or intermediate infrared bands. So when we talk about spectral band channels, resolution or characteristics, we are talking about the number of bands and in which area or range of the spectrum are located. For instance, when we talk about multispectral sensor, we are talking about sensors with 3, 4 until 10 or 30, 20 bands. But when we talk about hyperspectral sensor, we are talking about sensors with more than 200 bands. With hyperspectral sensors, we have an image for each band, so we can obtain profiles of reflectance in each band and then characterize the different sort of soils, water, vegetation, or any other sort of material targeted. Spectral sensitivity is the relative efficiency of detection of light or other sort of signal as a function of the frequency or wavelength of the signal. So we can have a sensor with the same ground sample distance, the same swath, with several hyperspectral or multispectral bands, but with different sensitivities for each band, with different efficiency in terms of detection. For instance, normally the visible and near-infrared detections are more sensitivity at visible bands than in the near-infrared bands. When we represent graphically an impression of the distribution of data, when we represent for each band this distribution, we have an histogram of the images and an histogram for each band. So then, and using the dynamic range and the saturation of this range, we can adjust finally lookup tables or curve how better represent the images on the left hand side captured by the sensor, and finally, thanks to the acknowledge of these histograms and taking into account the dynamic range, how to represent the image to improve the contrast, improve the range of values at the targeted interested point in terms of the application and usability. The image represents the key element of usability in any Earth observation, architecture and strategy. So to talk about the image is to talk about different sorts of resolutions: spatial, spectral, temporal and radiometric resolution. The slide represents different examples of spatial resolution. So now it's quite obvious to define the image resolution as an umbrella term that describes the details an image holds. So a basic concept is to know that higher spatial resolution represents more image detail. So nowadays the term resolution or spatial resolution is often used for a pixel count, GSD, or ground sample distance in digital imaging. There's several methods to define which is the spatial resolution of a certain sort of instrument or sensor. However, the main concepts to be defined are related to the relationship between spatial resolution and the capacity of photo interpretation. So let us to define the following concepts: detection, discovery of the existence of an object but without being able to recognize; recognition, assign an object to a class, or just the identification, discrimination between objects of the same class. So, to define from an user or usability point of view, the Earth observation architecture has a useful tool is to define with the end user which will be the levels of detection, recognition and identification required for this application or usability. So, if only detection is required or recognition is required, we use high, medium or very high resolution images. At this example, for the same area, the harbor of Barcelona, we have from 3 different sensors at 3 different satellite platforms the same targeted zone. If identification is required by the end user, we must use very high resolution images just below 2, 3, 4 meters. If only recognition or detection is required by the end user or for the application, we can use medium or just very high resolution images. What about the spectral resolution of the images? As it has been mentioned previously, it's a measure of its ability to resolve features in the electromagnetic spectrum, and obviously is related to the number of bands. So many bands we have, many possibilities to find, obtain the spectral signature of an element. If we have 288 bands, 144 bands, 96 bands, 26 bands, or for instance 3 or 4 bands, is more difficult to recognize all the characteristics and behaviors of the different sorts of covers, materials, and so on targeted at the image. Temporal resolution is related to the frequency or amount of observations images along the time. At part 1 of this tutorial, we could see that temporal resolution is very dependent of the satellite or platform and sensor characteristics. Temporal resolution is very related to the usability or the application. For instance, environmental, surveillance, or safety and security applications require a very high temporal resolution. However, some other sort of applications, like in hazards or emergency, temporal resolution becomes not a key element because it's more important the reactive time, how long we can respond to a certain hazard and just take an image. Digital range will drive the radiometric resolution of an image because it's addressing finally the number of levels to be represented. At these images, we can see shadowing zones where, depending on the dynamic range of the sensor, we can obtain information or detection, recognition, identification, or not at the shadowing zones. At the end, this information, this multispectral or hyperspectral or several bands information, can be represented on a digital basis, but combining 3 of these bands on the red, green, and blue channels. So, according to the final selected channels or bands, we can obtain different combinations and different representations. If we choose the green band, the red band, and the blue one, and these bands are represented in the right visualization, red, green, and blue, we obtain an image that is close to our visual interpretation. However, and depending of the usability or the sort of applications, we can consider other combinations to detect, to distinguish, and to emphasize the sort of target that we can detect, identify, or recognize. Unsharpening is a method that combines high spatial resolution with high spectral resolution. Just because the majority of Earth observation satellite sensors capture image on panchromatic resolution and multispectral resolution, so in very high or high resolution and high or medium spatial resolution. As it shows in this image, we have a panchromatic image and a multispectral one. The left one is a multispectral image with a pixel size around 30 meters, and the right one is a panchromatic with a spatial resolution below or 5 meters. So we can pan sharp this image by using different methods just to obtain improved images in terms of photo interpretation, in terms of detection, recognition, and identification, by using from one side the better spatial resolution of the panchromatic image, and from the other side the spectral resolution to obtain an image on the visible wavelengths. Just to end this part of the tutorial dedicated to the image, a few words about the compressed and uncompressed format, or the sort of formats that the image can be downloaded and processed. We have uncompressed images, uncompressed ones. A compressed images will always below an uncompressed ones, and we have two different types of compressions, lossless and lossy. Currently exists a trend to use compressed image on board the satellite just to relax the transmitting budget, communication budget from the satellites. In terms of image file formats, also we can have georeference, inner or exterior georeference image, where no additional files are required to obtain a georeference image to be superimposed to other georeference information, data, images, and so on, or we have an exterior georeference file to process jointly with the original image to finally obtain a georeference data. Next to a slide summarize the main image file formats that we can obtain from satellite providers depending of the usability, the sort of platform, and the sort of sensor. To know previously this information should be paramount in terms to properly dimensionate the sort of end users' needs, applicability, usability, and the cost associated to process these data. To know the file formats that will be used in our Earth observation program also becomes paramount in terms to select the sort of software, open software or commercial software that will be used to transform this data, this image into information. We move to the last part of this tutorial called the mission. This part has been elaborated taking into account operational and demonstrative programs on the use of Earth observation as a tool for end users, decision makers, and scientists. The first example that could be or should be used as a summary of different concepts of this tutorial in terms of platform, sensor, image, is focused on light pollution. Light pollution could be understood as the luminance that escape to the sky and obviously is not properly illuminating the right target. So the municipality not far from Barcelona demands an Earth observation program to detect and to quantify this light pollution. So we need a very high resolution system in order to transform these digital levels into luminance by using a physical model. The need of a very high spatial resolution moves us to an aerial surveillance instead of a satellite one. A few satellite sensors are dedicated in terms of light pollution with spatial resolutions about 500 meters or just 1 kilometer. So these sensors are very interesting in terms to analyze demographic movements, economic activities along years and years, but not becomes a useful tool for an end user that needs to know if he is out or not of a certain normative levels of illuminance. We use an hyperspectral information to basically obtain luminance and transform this luminance into candles square meter, as well as to use the hyperspectral signatures to obtain values about the nature of this light. Sodium, mercury, lights, etc., etc. Here you have this information as a classified image about the light pollution, and on the right side some in situ measures on the ground to calibrate and validate this data as a paramount exercise to provide integrity and quality products and services. Next example is related to energy leaks and detection of materials. So, for this example, was necessary the use of long-wave infrared or thermal bands to detect energy leaks from industrial resorts. The same sort of application in terms of the use of thermal spectral bands is about downsize or lamp fields, where is necessary on a non-invasive methods, so aerial or satellite images will become a key or paramount approach to detect hot spots as well as the sort of gases emitted by these hot spots. Urban environment becomes one of the new and more important trends of usability of Earth observation tools. Here you have on an urban area 3 examples of use of different sort of spectral, spatial and radiometric resolutions. On the left hand side you can see a thermal images on an urban area where finally is derived information related to heat islands. At the center and right side you have information related to the urban green and how healthy is the vegetation in urban areas. At the end, all this information becomes layers of information to be analyzed and processed jointly to finally offer different sorts of emergency, forecast or no-cast service at urban environments. Next two examples are very performant examples on the use of satellite information to translate data into information and knowledge. Here you can see at different settlements information derived from radar satellites when the use of microwave spectral bands as well as good revisit times are used to finally provide subsidence movements of the territory. These movements could be related to the management of underground water reservoirs, minor activities, or other sort of hazards, and needs the interpretation of geological expertise to transform into knowledge. The second example is the use of multispectral at visible and near infrared bands to finally derive a service about if it's necessary or not a new fertilization on the crops and the subsequent economic effects. These sort of applications are known as precision farming applications and represent one of the key issues to summarize the use of multispectral or hyperspectral information from satellites with information from airborne sensors with a higher spatial and spectral resolution to calibrate the satellite images, as well as in situ information to modelize the agronomic model that take the image as input and finally obtain information about the levels of fertilization to be required. So the main characteristics in terms of platforms, sensor and images, as well as the main technical, operational and scientific concepts has been explained and summarized to finally be addressed as a set of mission examples where these concepts and fundamentals characteristics of platform sensors and images has been analyzed. Earth observation tools and technologies, a world to be sensed.